Okay. Welcome, everybody. Good morning, good evening, good afternoon. It is my great pleasure to introduce Daniel Larremore. He is an assistant professor in the Department of Computer Science and the Biofrontier Institute here at the University of Colorado Boulder. His research develops statistical and inferential methods for analyzing large-scale network data and uses those methods to solve applied problems in diverse domains, including public health and academic labor markets. Prior to joining the university here, he was an Omi Dyer Fellow at the Santa Fe Institute and a postdoctoral fellow at Harvard School of Public Health. He obtained his PhD in applied mathematics from CU Boulder. Among his many honors, Dan was recently awarded the NSF Alan Waterman Award, the nation's highest award or honor for early career scientists and engineers for his work on computational epidemiology during the height of the COVID-19 pandemic. Dan, it's an honor to have you here, and please join me in welcoming Dan.
Thanks so much for the invitation, and I'm really excited to be here. So let me share screen and give you some idea of what we'll talk about today. So I want to tell you about the view of my group in close collaboration with Aaron Clausette's group in our study of the science of science. And in particular, while many others are very interested in fascinating work on citations, on how we search for information as scholars, what my group is primarily interested in is understanding people as the fundamental unit of analysis. And that means that we often study faculty, postdocs, and graduate students because we're very interested in people. And what I'll tell you about today are some fresh results. I haven't ever presented these results before, so I hope it goes okay. We'll talk about quantifying hierarchy and dynamics in US faculty hiring and retention. And in particular, while I'll discuss some of our findings today, because this is a summer school, I want to give you some idea about the methods that we use along the way. Here's our premise. Our premise is that faculty really shape the scientific ecosystem. They work on making discoveries, so they're doing science. They work on training students, so they're part of the research ecosystem. They teach courses at universities very often, so they're involved in education. They communicate science to the public, and they advocate for research priorities to their representatives, so they're involved in policy as well. These processes are therefore directly affected by who faculty are, by the structure and dynamics of faculty hiring labor markets. And so today's investigation is really motivated by these bullet points at the top, asking just what can we say about the broad patterns that shape this population. So to find out, we analyzed employment and education data for around 300,000 tenured or tenure-track faculty across 368 PhD granting institutions, spanning all fields. And we had snapshots of data over 10 years, 2011 to 2020. So the goals were to really understand what's going on with faculty. So we start with a descriptive analysis. So the first question we could ask is, where do US faculty come from? Oh, nope. Oh, shoot. Why did it go that way? I think I have right click turned on. That's embarrassing. Sorry, guys. Okay. So here's the descriptive analysis. Where do faculty come from? First of all, we divided academia into 8 broad domains based on the department that professors were sitting in. And we also looked at academia as a whole. And this is where things look like for the US. You can see on this chart that we have proportionally a large fraction of faculty getting doctorates from within the US, actually a reasonably large fraction of faculty with no doctorate, and a large fraction of faculty with non-US doctorates, although of course the largest portion is still those with US doctorates. At the broad level, 92.7% of faculty in the US hold a PhD or some equivalent. But this varies a lot by field. So in terms of credentials, only 1% of professors lack a PhD in the social sciences versus a 19% in humanities. And I want to just start things out with some engagement. So does anybody have any guesses as to what field, not one of these 8, but one of the fields that make it up, what field has the largest fraction of faculty that doesn't have a PhD? What fields can you think of that don't require that as a credential? I see English, I see art and fine arts. Thank you, Mary and Sarah. Religious studies. These are great guesses. Okay, I'm going to reveal the answer. On the vertical axis, you can see the percent of faculty without a doctorate. And on the horizontal axis, we're just grouping by these domains. And we've just labeled any of those fields where there are large fractions without PhDs. So these are great guesses. In fact, philosophy is a field where you almost certainly need a PhD in the US. But art was a great guess. Art history, architecture, theater, music, urban planning, nursing. These are fields where some professional expertise is apparently more valued than a doctoral credential. Performing arts, yes, Yaz. Great suggestion. Okay, so we know that you generally need to have a PhD, although there is a lot of heterogeneity by field. We also observed that 11% of faculty have non-US doctorates. Now, this is different from saying that faculty come from institutions outside the US and train in the US. We know that that takes place, but actually our data can't tell us what people's national origins are. But what we can see is that 11% of faculty have doctorates from outside the US, but again, we see variation. So in education, only 2% of faculty have non-US doctorates, whereas in the natural sciences, it's 19%. So in terms of the labor markets for US academia, we can see that the natural sciences is much more open to credentials from outside the States than education. Okay, so we can now ask, where do faculty who were trained abroad actually come from? So we investigated this specifically, and here's the chart that we end up with. What I'm showing you are those 8 domains that we divided departments into, and we're grouping by continent broadly, so Africa, Asia, Europe, North America, Oceania, and South America. And in darker shades, we've simply colored in those who are trained in the UK and Canada. And this is important because faculty trained abroad come from generally a restricted geography. So 35.5% trained in the UK and Canada, and just 5.3% trained in all of Africa and the Americas, excluding Canada, and of course the US combined. So you can see that there is substantial heterogeneity here and also substantial inequality. Most faculty are trained in the US, and most of those who aren't trained in the US are trained in places other than Africa and the Americas. So there's substantial inequality in the system. Yaz asked a question in chat that I want to address, asking, non-US, does this mean that they were born outside the US or that they studied outside the US? Specifically, this means that they got their PhD outside the US and were then hired as professors inside the States. Unfortunately, we don't have national origins, passport, citizenship, anything like that for these professors. So the only thing that we have visibility on is where did they do their doctoral work. Thanks for the question. Okay, so I'm curious to hear what you think. What other patterns do you see in the data here? And what questions are you curious about to ask if you had this detailed data? Any thoughts? Oscar asks about change over time. That's a great question. And in fact, let me answer a version of that question now. We're going to ask, does it matter where you trained? And specifically, does it matter where you trained for what you do in the US academic system? So to think like demographers, we're going to do more than just analyze snapshot or cross-sectional data. And instead, we're going to look at longitudinal data. So we're going to look at the same system over time. So one question that we can ask is whether attrition varies by location of training. Attrition means people who were professors, but then chose to leave academia and take a job in industry. We can quantify attrition via a risk calculation. And I want to introduce risk here for those who are unfamiliar. The way that we calculate risk is really simple. It's just a ratio. It's the number of events, here the number of people who left, divided by the number at risk. So here's just an example calculation. Each dot in this little diagram represents a person, and I put them in the same place in each of these time slices. So you can see that in 2011, there were 4 of these teal professors, and then one of them left. But we also gained 2 blue professors. And then in the next year, one of the teal professors left and one of the blue professors left. So in total, we see 4, 5, and 3. But of course, we know that we can't just analyze the total number of professors. We need to analyze who was there and available or at risk of attrition and who actually left. So if we calculated the number of events and the number at risk, in terms of events, we could see 1 attrition event from 2011 to 2012, and then 2 attrition events from 2012 to 2013. If we're looking at the number at risk, that's the total number of professors in 2011 who could have left, and the total number in 2012 who could have left. And adding this up, we see that there were 3 total events and 9 person years at risk. And so we conclude that the annual per capita risk of attrition was 3/9, or 1/3. Okay. So another thing that we can ask is about a risk ratio, and that's exactly what it sounds like. It's the ratio of 2 risks. So we can define a risk ratio as the risk in population A over the risk in population B. So let's say that I have this group in the upper right. I know that their risk is 3/9. And in population B, I can look at those faculty and do the same calculation. And here I get a risk of 5 attrition events over 11 at risk. Forming the risk ratio, I have 3/9 over 5/11, and I can reduce that down to 11 over 15. So my questions to you now are, how can we interpret this value, 11 over 15? What does this mean? And the second question to you is, why might we leave our fractions here unreduced? Why is this fraction, 3/9, 5/11, useful to us as scientists, in addition to just this number reduced, 11 over 15? So I'll give you a second to think. Feel free to chime in on audio if you like, or chat is also fine. I have that up here. Any thoughts on what the risk ratio means? How should we interpret 11 over 15? Okay, well, because we don't have all the time, I'm going to jump in with some answers here. Here we have an answer from Daniel. Thank you, Daniel. If this number were greater than 1, then the population on top would have a higher risk than the population on bottom. If the population, or if the ratio is less than 1, then the population on bottom has a higher risk than on the top. So this is telling us that population B is at greater risk than population A. Yaz also says that the risk in population A is 11/15 of the risk in population B. That's also a totally correct interpretation. I want to answer the second question too. Why might we leave our fractions unreduced? This risk ratio tells us about the numbers, the relative risks. But if I want to do statistical testing and decide whether or not 11/15 is a significant difference between A and B, I need to know my sample sizes. And so when I'm going to do my chi-squared calculations for significance, it really helps to have these values handy instead of always reducing them to the fraction. So that's what we're going to see on the next slide. So does it matter where you trained? Here I'm showing you risk ratios. So this is relative annual attrition by doctoral origin. And I'm comparing 2 groups here. Group A is Canada and the UK trained professors, and Group B is US trained professors. And what you can see here is lots of variation in risk ratios. But when we do the statistical testing, these X's indicate that none of these ratios were actually statistically significantly different from a ratio of 1, except this one at the level of academia, which slightly indicates that those from Canada and the UK are at less risk of attrition than those from the US. On the other hand, if we look at 2 different groups again, those trained outside the US, excluding Canada and the UK, divided by those in the US, you can see that now we see almost across the board, except for some non-significant values, elevated risk for those who are training outside the US. So what this means is that if you are a US professor and you got your PhD in the US, Canada, and the UK, you're at a generally baseline risk for leaving the academy. However, US academia loses talent trained from abroad outside of Canada and the UK at significantly, and in this case, substantially higher rates, 6 to 4. That means 3 professors leave from outside the US, Canada, and the UK for every 2 from the US. And so, you know, if you're interested in talent and in where ideas come from and what perspectives people are bringing to what they study, I think this is an important result. So it does matter where you trained. We don't know why there are these differences, but establishing that the differences exist is a good first step. Okay, where do US trained professors come from? This graph is showing the percentage of faculty who are produced from different institutions in the US versus the percentage of US universities we include in the sample, and we've sorted this. So the top 8 universities, in terms of how many professors they supply to the rest of the system, supply 20% of the faculty. The next 20% of faculty have PhDs from 13 institutions, and 308, or 79.6% of institutions, produce this last 20% of faculty. So there's substantial inequality in the system. And another way of putting this is that 1 in 8 faculty, so 13.8%, were trained at just 5 institutions: Berkeley, Harvard, Michigan, Stanford, or Wisconsin. So this is a way of just visualizing the amount of inequality in the system. Yes, we know that most US professors get their PhDs from the US, but it turns out that 20% of them come from just 8 institutions. So there are ways that we can analyze this in more traditional ways coming from economics. One of those ways is the Lorenz curve. So I told you that I wanted to show you some of our methods. So here's the idea behind the Lorenz curve. We're going to sort in some economic system here the supply of faculty to the academic system. We're going to sort producers by the percentage that they produce from high to low. We then compute the cumulative percentage produced, and we plot cumulative producers versus cumulative production. So that means that we're going to have on this horizontal axis the percentage of institutions included in our sample and the percentage of faculty produced on the vertical axis. And I can put 2 points on here for free. I know that 0, 0 has to be on here because if you give me 0 institutions, I know for a fact that you've produced 0 faculty. Similarly, if I give you 100% of the institutions, I know that you've produced on 100% of the faculty in the sample. And if every institution that I include produced the same amount of faculty, then I would get this diagonal line. This is a line of perfect equality. The slope is a constant, and so each marginal institution that I include gives me the same marginal increase in the percentage of faculty produced. That means that if some institutions are producing more than average faculty, I should see a curve that goes above this line. And this would be a curve that we're going to label inequality. If the system is more skewed and more unequal, then I should see stronger inequality and a line that is even farther up, crowded to the upper left. So just as some background here, because it's interesting to learn history, this is named after Max Lorenz, died in 1959. The curve came from his undergraduate thesis. He then did his PhD at Wisconsin-Madison. He did not name the curve after himself. Another economist did that. And Max Lorenz apparently did not become an academic. I don't know exactly what he did. I think he worked maybe for the Census Bureau after this. But anyway, so what we're going to do is draw these Lorenz curves for every field in our sample. And here's what they look like. So now I have these 8 different domains, and each one of these light lines is a different field. The gray line is when we aggregate those fields up into a domain. So what you can see here is they're all far away from that inequality, or sorry, far away from that equality diagonal line. All of those fields are showing substantial inequality in where faculty come from. I put a dot on where the domain curve intersects with 80%, because you've often heard perhaps this Pareto principle, the 80-20 rule, that 80% of something is produced by 20% of something. And here you can see that anytime the 80 and the 20 line up, that means that this domain is really checking that Pareto box of 80% of faculty coming from just 20% of institutions. Pretty clear that applied science is close. Humanities is, in fact, more unequal than an 80-20 rule. But all of these are not too far away from that. Okay, this requires that we show curves for every field to quantify inequality. But we can also summarize these curves using something called the Gini coefficient. So if I take one of these Lorenz curves and I draw up two areas, area A is above the curve and area B is between the curve and the perfect equality line, then the Gini coefficient is simply the size of B over the size of A plus B. So when G is equal to 0, we get equality. In other words, the pink line has shrunk all the way down to the perfect equality line, so B is 0. On the other hand, G equals 1 is when B totally crowds out A, and we have perfect inequality. So one university produces all the professors. Okay, it's important to know some history here, and I'm going to throw some cold water on any excitement you have about Gini as a person. Corrado Eugeni was a eugenicist and a fascist. And this I thought was just bizarre. I had no idea about this. He was part of a movement that wanted Italy to be annexed by the United States after World War II. So I don't know what to make of that. But this is a good example of the fact that before the invention of research ethics and before a focus on inequalities and these things, you had a lot of assholes out there. So part of my judgment of Corrado Eugeni after his passing, but yeah. Okay, the Gini index is widely used by economists, typically to look at things like income disparity. So if you take the Gini coefficient, multiply it by 100, and instead of looking at faculty production, you look at income, annual income, and instead of universities, you're looking at people, you can see that in Mexico and Brazil, you have high Gini coefficients, so more inequality in income. The United States, China, France at a time in the middle here. And toward the bottom, you see Norway, Bulgaria, Belgium, Italy, Canada, Germany, Poland, Sweden, France. Lower inequality in income there, but still, some substantial inequalities there. But I want to give you a sense of scale. When you think of inequality in income in the United States, the United Kingdom, Mexico, Brazil, think about Gini coefficients between 30% or 0.3, 60%, 0.6. Now let me show you production of professors in academia. All of these across domains are above 0.6. Some are even crowding towards 0.8. So the Gini coefficients across fields and across time are all large. They don't appear to be growing or shrinking over our decade of observation either. But I can actually look at the Gini coefficients in two different groups. Let's look at just new professors, see where they're coming from, and just sitting professors and see where they came from. What we do when we do that, plotting new faculty in the dark circles and existing faculty in the open circles, is across all the different fields that we looked at and across the domains in these larger bars. Faculty production is less unequal for new faculty compared with the existing faculty. So what might explain these patterns? One hypothesis might be that new faculty are simply hired in a more equal way, although this is still pretty unequal, but a more equal way than older faculty, and that this has been changing over time. But actually what we find is something slightly different. What we looked at was again, annual attrition risks. What we found was that annual attrition risks are higher for professors who graduated from institutions that are lower in production rank. In other words, if you are US trained and you come from an institution that typically does not supply many faculty to US academia, the risk of attrition for that group of faculty is higher than those who are coming from Berkeley, Wisconsin, Michigan, and those other institutions that supply a lot of faculty. The way that we present this is, again, by showing average annual attrition risk, but now we're sorting this by production rank. And each of these curves, again, represents one of the domains. And so if you compare the leftmost point, that's coming from like a Berkeley, to the rightmost point, that's coming from a place that supplies very few faculty, you can see that the risks are almost twice as high for those faculty who are coming from those less producing institutions. So this means that there's substantial inequality in faculty hiring, and that's exacerbated by attrition. So the attrition processes magnify inequalities in the system. So let's talk about differential attrition risk and what this actually means. Where these curves come from is to use logistic regression to analyze the data that we have. Now, the data that we have is either 0 or 1, depending on whether or not somebody leaves, which we're going to call a 0, or somebody stays, that's going to be a 1 in each year of our observation. Now we're going to say that xi, our covariate here, is the rank by production. It's just sorted by faculty produced of that institution that I graduated from. We're going to fit a very simple logistic regression model so that the logit of yi is just some intercept plus a slope times that institution's production rank. Because the beta 1 values that we find are positive, that means that a higher production rank means higher risk. I'm also noticing that I flipped the 0 and 1 here. So people who leave would have been a 1, people who stay would have been a 0. But essentially, these curves are then the fitted curves of these logistic regressions, not in logit space, but in regular space. And we found these to be a little bit more interpretable than just plotting those coefficients. Okay, so one reflection here is that examining just one of these plots alone would have led us potentially to an incorrect understanding. And it's helpful to analyze both the differences in cross-section, changes over time, and these annual risks sorted by production rank. So we're going to do the same thing for gender. For all of these faculty, we either knew their gender because it was self-reported, or we analyzed their names using name, gender, cultural associations. And here's the picture here. Over our decade of observation, you can see that women's representation across academia in blue or across all of these domains steadily going up. And in fact, when we do the stats on this, we see that all of these are statistically significant increases over time. However, if we look at the gender ratio among those who are new hires and the gender among those who are leaving academia, either for retirement or leaving academia before retirement, you see, again, huge differences between these groups. So the folks who are coming into US academia are by and large far more likely to be women than those who are leaving academia. And when we analyze the demography of all of these different domains, we see a really interesting pattern. If you look at career age, so these are people who are 1 year out of their doctorate, versus those who are near retirement, these are 40 years after their doctorate, you can see that across fields, the younger faculty are more likely to be women, the older faculty are more likely to be men, but I'll still note where the 50-50 line is here. A lot of these fields are very far from parity. So what explains this interesting plot in the middle is not a story about hiring, but actually a story about retirement. US academia, the old, generally male cohorts are retiring. There are very few women relative to men among those cohorts. That's why these segments on the right are so low. In contrast, hiring is much closer to being egalitarian, although, again, if we look at something like engineering, still very far from it. So you might think, if you looked at panel A, that this situation is improving. And I think from one perspective, you could argue that it is. We're moving toward parity. On the other hand, if not for panels B and C, we would misunderstand panel A. What I'm not showing you here is that women's representation among only the new hires, so these dots on the left in the middle plot, if you look at those over time, that's been flat for 100 of 107 fields over the decade, and it's actually significantly decreased for the other 7. So the big takeaway here is that women's representation in the US Academy has been increasing over time, but that's been driven by retirements, not by substantial changes in new hiring. And in fact, if you look at fields like math and computing, engineering, applied sciences, natural sciences, these fields have not been substantially changing their hiring practices over the past decade, which means we're not going to see future parity in US academia unless hiring continues to change. Essentially, what looks like an improvement is actually the bearing of fruit from the efforts of past generations. Okay. Yaz asked a question in chat that I want to address, which is, can you please explain production rank one more time? I'll go back to the previous slide just to give some context for this. So when I talk about production rank, what I'm going to do is take all of the institutions out there, and I'm going to look at how many professors they supplied to the US academic system. How many PhDs did they graduate who then went on to become professors? So Berkeley produced a ton. Michigan, a ton. Stanford, a ton. Harvard, also a ton. Wisconsin, a ton. And I'm going to sort them from those that produced a lot all the way down to those like University of Colorado that produced some, but not a ton, and down to universities that most people have never heard of because they don't produce that many professors who go on to teach classes and expose people to where they got their degrees from. So when we talk about production rank over here on the left, these are the institutions that produce the most faculty, and those over on the right are those that produce the fewest. Marcia asked a question. Oh yeah.
May I continue? Sorry.
Yeah.
As I know, the size of the university is really a matter to whatever the rank is, because maybe think about this situation that the university has only maybe 20,000 or 100,000. They are really different from each other. Should it be normalized to the number of the size of the university? Means that wasn't it more real if we just did that?
Sure. So if I understand your question right, you're saying, well, look, Berkeley is huge as a university. It has a lot of faculty. Of course, it's going to produce more professors. In fact, your intuition is correct in that we see a strong correlation between the size of the institution, measured by the number of sitting professors, and the number of faculty produced, so it's sort of the export of professors. However, the faculty size alone can't explain the amount of production at an institution. So there's something more going on than just a larger faculty producing more future professors. They're correlated, your intuition is great, but they're not exactly the same. And we'll get to one of the ways in which they're not the same in the next couple of slides. Marcia, I want to address your question. Marcia asks, do I understand correctly that positive discrimination strategies did not increase women's hiring in the US? I would say that understanding is not quite correct. What we're seeing when we look at, let me go to the next slide, these gender inequalities, is that actually efforts to change how we hire have dramatically changed. I mean, if you look at the demography over here on the right, you can see that the old cohorts were really strongly predominantly male. And as you look at younger and younger and younger cohorts, you can see that they're more likely to be women. However, what I'm saying is that if you look at just the new hires, I should just make this plot, but if you look at just the new hires and plot them, like over here on panel A, they're all flat. That out of 100 or out of 107 fields, 100 of those are flat, and in 7, women's representation among new hires has been decreasing. But that's only over the past decade. So what you can see here is that efforts in the 1990s, the 1980s, the 2000s, these really changed things for older cohorts, but more recent progress has been flat. And my interpretation is that if recent progress has been flat, and these kinds of numbers over here on the left represent what we're doing currently in terms of hiring, most of these fields are far from parity. So we're not just seeing like equality in hiring and now things are working their way through the demography. In fact, we're seeing still inequality in hiring. And yes, things are working their way through the demography, but in a lot of these fields, we're nowhere near parity. Okay, I want to talk a little bit about faculty hiring networks, because one of the big things we do in my group is think about networks in lots of different applications. So one thing that we can do with hiring is, instead of looking at these sort of summary statistics, we can create a network where we have directed flows of faculty from their PhD institutions into where they're now professors. So this is just a snapshot of a computer science faculty hiring network. These are 10 institutions. And you can see that I've highlighted the flows out of MIT. So these are flows, these are people who got their PhDs at MIT. You can see this network is complicated. People got their PhDs at lots of different institutions, and we see this network of exchange. And if we take some premises here that each hiring committee wants to hire the best, whatever that means, that's up to the hiring committee. Then if I zoom out and look at the entire faculty hiring network, I can understand something about the collective preferences of institutions when it comes to hiring each other's graduates as faculty. What this allows me to do is look for a social hierarchy here. If there were a perfect social hierarchy, no institution would hire from any institution less prestigious than their own. They would only seek those faculty who are coming from more prestigious locations. What we can ask is how well aligned is the actual faculty hiring network with that idealized perfectly strict social hierarchy. And we can do that and create a ranking not based on things like what US News and World Report or Times Higher Education cares about, but instead just analyzing the preferences of the institutions for each other's graduates. And so we end up with sort of a sorted network ranking from high to low. The idea of rankings is really pervasive, so I want to go on a slight detour here. Oftentimes when we rank things like sports teams or chess players, we think that competitors have some kind of intrinsic quality or vector of qualities that we hope to identify. Interactions between them can stochastically reveal differences in qualities, and competitions are pairwise. So if I think about Lee Sedol playing versus AlphaGo to see who's better at Go, they played a series of games. When the Astros play the Dodgers in Major League Baseball, they play a series of games to see whether or not we can determine which team is the better team. Another way of saying this is that outcomes are generated by some kind of stochastic process, which is some function of the positions of the competitors. And so we see this in lots of different fields, lots of different areas. And I want to just kind of give some sense that we see this in terms of systems of dominance, like in social systems of dominance, where birds are literally pecking each other off of these cliffs that contain a clay that has some minerals in it. Games of mental dominance, like Go. Games of physical dominance, like people fighting each other. Or games of sort of financial strategy where teams are trying to accumulate a group of players that are going to beat each other. We often think about ranking in terms of these kinds of systems naturally. You rank the sports teams, you figure out who is the champion. But we also see this in systems of endorsement. And I just want to point out that the assumptions are really similar here. Our assumptions here are that endorsers have some kind of intrinsic quality, where quality here is not a judgment, but just stating that these institutions think of each other having some kind of prestige. The interactions between them, we believe, can reveal pairwise difference in those qualities. And the endorsements here are pairwise. Faculty are hiring directly from each other. So one of the things that we can do is then try to rank this. And this ends up being a directed network problem. We have some adjacency matrix A that says I to J is that I beats J, or that I was endorsed by J. And the problem here that we have is to rank the nodes. I'm going to jump through this because I want to get to some of these questions. We have a bunch of different ways of ranking, but I'll show you what happens after we complete these rankings. Is that what we end up with is an embedding, and we can apply these kind of network methods to lots of kinds of systems. So for instance, you can analyze networks of rural social support, where you ask people, who would you go to if you needed help with a meal or help finding a job? This is work done by Eleanor Power in South India. Elizabeth Hobson works on literal pecking orders of parakeets and enclosures, looking at their dominance interactions. We can rank those as well. And of course, we can look at faculty hiring networks. And the thing that all of these have in common is that we've identified the vertical position, where top means top of the pecking order, and all of the flows that are moving down the network are on the right, and all the flows moving up are on the left, red. And we also can look at the positions of the nodes in these different systems. Okay. So using these network methods, we can look at faculty hiring networks and look at the prestige change from where you got your doctorate to where you are currently as a professor. And across academia, the mean change is to move about 18% down the prestige hierarchy. So at the academic level, 18% of faculty move up, 11% are self-hires. There was a question about this. 71% move down. And there's some variation of this by domain as well. So 71% move down, 18% move up. That's a 4-to-1 ratio of people moving down this prestige hierarchy. The steepness varies from field to field. So in humanities, there's a much more strict prestige hierarchy where 12% move up. In math and computing, 13% move up, versus medicine and health, you can see 21% move up. What this means when we combine this, what we know about production inequalities, is that the typical US trained professor will supervise nearly 2.5 times fewer faculty than their advisor did. One important question, however, is how much of the steepness is simply because we've ranked a network with a broad out degree distribution? In other words, how much of this is just driven by the placement inequality? One thing that we can do here is use something called the configuration model. This is a model for networks where we draw a network that is random, but we fix the in and out degrees. So to Yaz's question earlier, we fix the production and we fix the faculty size, and then we wire up the network randomly otherwise. We can ask, does production inequality explain prestige inequality, or is prestige something more than just differences in production? So this figure answers that question. What we're plotting here is the percentage of up hierarchy hires in the empirical data and the percentage of up hierarchy hires in a null model. And oh gosh, I think these are, yep, these labels are switched. Sorry about that. Essentially, what we find is that across fields, you see more up hierarchy, or sorry, these aren't switched. In the null model, there are more up hierarchy hires than in the empirical data. In other words, when you just randomly wire the network but fix the faculty size and faculty production, you actually end up with flatter hierarchies than in the empirical data. There are a couple that don't follow this, like pharmacy is an example. For the most part, most of these fields do. So that's for 8 out of 8 domains for academia as a whole, and the vast majority of fields. The real networks are significantly steeper than their randomized counterparts. One other thing that we see from a network analysis is that we have an elite core of exchange among the top prestigious institutions who export to the periphery. So what I'm showing you over here on the right is the mean geodesic distance from any institution at a particular prestige rank across that hiring network going to any other institution. So what you're seeing here is that the distance from an elite institution to all of its peers is much smaller. So elite institutions are a lot closer to other institutions than those who are toward the low end of university prestige. So this means that prestigious institutions are closer to others in the faculty flow network. Because of production inequalities, we also know that these institutions on the left are not only closer, but these are net exporters of faculty. And because of the prestige inequalities, we know that this means that the core largely exchanges faculty with others in the core while exporting faculty to the periphery. However, we know that because you rarely move up the prestige hierarchy, faculty only rarely move from the periphery to the core. My colleague Aaron Clausette often refers to this as a homeland and colonies type of effect, where you have a homeland where there are lots of exchange of faculty here, and they often move from the homeland to the colonies, but rarely move from the colonies back to the homeland. So it's sort of a one-way dynamic. Guys, I got too excited about this stuff, ran out of time a bit. I want to tell you just a little bit about self-hiring. That was a question. A self-hire is somebody who's a professor at the same place they did their PhD. The literature does not look kindly on this. They often call it academic inbreeding versus biologist outbreeding. In the literature, they often discuss this in the international context and talk about how this may be also a signature of smaller or developing university systems. And sometimes people are talked about being silver-corded self-hires. These are people who are self-hires but left for a while and came back. I say, for example, here, because I got my PhD at the University of Colorado, I'm a professor here now, so I would be a self-hire, but because I left and did a postdoc elsewhere, the literature would refer to me as academically inbred, but silver-corded. Okay, fine. Rates vary a lot internationally. 36% of Russian academics are self-hires, 67% in South Africa, 73% in Portugal. So what about the US? Well, in a faculty hiring network, a self-hire is simply a self-loop, so a link from I to I. When we look at what we see in the US, there are 3 important points. The first one is that self-hire rates vary substantially by field. So again, you can see the different domains here. Humanities, very low rates of self-hire. Medicine and health, substantially higher rates of self-hire. We also see differences by gender. So men are hatched, women are in the filled in, and overall are in these empty panels. So we do see substantial differences by gender, but we see more variation by field and less so by gender. Second important point is that self-hire rates are all much larger than we would expect under the configuration model for a randomized network null model. Those are these dots here. You can see that these dots are all uniformly much, much, much smaller than all the bars. So self-hiring is driven by some process other than what we would expect based on our null models. The other important thing that I want to point out is that self-hires are often at substantially higher risk of attrition than non-self-hires. Again, looking at relative annual attrition, you can see that there is one field in medicine and health where self-hires are at lower risk of attrition, but almost across the board among those who are significant, we see self-hires at higher risk of attrition. So I've taken too much time, but let me just quickly summarize. This has been a story of inequality, attrition, and hopefully a little bit of methods. We find that most US faculty come from a small number of US institutions. The hierarchy of prestige is strong. Most hires are down the hierarchy. We also find that women's representation is increasing, but this is really due, in my opinion, due to efforts of generations past. We're not headed toward parity without continued efforts in this area. On the attrition side, we see a higher attrition rate for those who are self-hires, trained outside the US, UK, and Canada, and graduating from institutions that don't produce many profs in general. And in our latest work that I didn't have a chance to talk about, we also see substantially higher per capita annual attrition for women at every career age and stage. And this bullet point is one of the reasons that I believe that we need continued efforts in this area, not just in hiring, but also in understanding the reasons that people leave academia. In terms of methods, we looked at risks and risk ratios. We looked at Lorenz curves and Gini coefficients. We used logistic regression, took a network perspective, used the configuration model to analyze that network perspective, and used a method called spring rank to analyze the strata of hierarchy and prestige in the networks. So it's been a long tour. Thanks for letting me present today. I'll just put some references up here in case you're interested and acknowledge my primary colleagues on this work, Hunter Wapman, Sam Zhang, and Aaron Clausette, who we'll hear from in just a few moments. Thanks for your time, and I'll be happy to answer any questions if we actually have some time. Sorry for going over. Thanks.
Thank you so much, Dan. This is amazing work. It's a really interesting body of work, and of course we have time because we have Arunas here. He said that he is okay with a little bit more time. So please, if you have questions, unmute yourself. But first, let's thank the speaker. But please go ahead.
Any questions to start, or should I just jump into chat?
Yeah, you can read from the chat or
Yeah.
I have one question.
Yes.
Okay.
Oh, sorry, go ahead.
Sorry, my question was just in the chat. You can go forward. I can also come back later.
Okay.
I have one question, Dan.
Yeah.
So my question is that you have seen this, you have showed us this distribution, but I'm wondering how, like, what are the ideal distribution? Like, if we can change this policy, or we have something we can do for it, how should the distribution look like?
That's a great question. First of all, Yas, I see your question in chat. I'll type an answer after this oral part, and can give you some references on geodesic distances for networks. I liked your question a lot because it really gets at maybe more of an engineering perspective. So what we're seeing here are huge production inequalities, big gender inequalities, big prestige inequalities. And you could ask the question like, well, if you were designing the system, how would you design it? The first thing that I would say is I would not design the system with gender inequality in there. I think that if engineering is hiring 3-to-1 men to women, we're missing out on a huge amount of creativity and talent from half the population. And that's in addition to, I think, the ethical reasons that we would want something closer to parity. So from an engineering perspective, I think the gender inequality is problematic. In terms of prestige, prestige has an interesting effect on the system, which is that it ends up sorting people into sort of different bins, and people in those different bins get different amounts of resources. So for instance, we know that there's far more funding higher in the prestige hierarchy, far less funding lower in the prestige hierarchy. In studies of double-blind versus single-blind peer review, those with high prestige credentials have an easier time getting their papers published. And when you remove the credentials and make submissions double-blind, you see that those from high prestige institutions are somewhat equalized with those coming from low prestige institutions. So I think that while there may be a reasonable case to be made of matching very talented professors with very talented students and having some kind of prestige notion, I think that the system is far magnified beyond its usefulness. These examples of double-blind versus single-blind peer review suggest to me that people are relying too much on prestige as a signal, and they're treating it as something more than the meritocracy that they hope that it would represent. I think it's actually a way of sort of entrenching some inequalities, and we would be better with a somewhat flatter prestige hierarchy or less reliance on it. Okay, I did the professor thing where you asked me a short question and then I gave you like a 5-minute answer. Sorry.
That's great. Thank you so much.
So we have a couple of minutes for a couple more questions.
Let me take one from Marcia in the chat, which asked, can the higher attrition of non-US trainees be due to the fact that they leave the US? Marcia, what I would love to know is where are these professors now, to be able to sort of pick up where we left off and figure out where did they go. So here are a few possible scenarios. One is that they took better jobs outside of academia. We know that jobs outside of academia typically pay better than within academia. So maybe they were just pulled out. Secondly, maybe they went back to their country of origin or somewhere else outside the US. A third possibility is that they simply left our sample frame. So our sample frame was looking at all PhD granting institutions in the US, but there are lots of other institutions in the US. For example, a lot of liberal arts colleges don't grant PhDs, but they do employ professors. So it's possible that some of these people who we're looking at as attritions are just attritions for our system, but they're still within academia, just in a different part of academia. Oscar points out several countries have programs to regain the grads from other countries, especially from the US. That also makes a lot of sense. So it'd be great to find these people and maybe ask them, why did you leave? Let's see. Eric asked a question, how do you handle an institution hiring their own graduates? Are there some that tend to engage in that more than others? So what we saw was substantial variation in self-hiring by field. Let me pull this back up. We see differences by field. We see differences by gender. We don't know how to explain any of these differences. Why would it be that in some domains, like in the humanities, self-hiring rates are low, whereas in the applied sciences, they're higher, engineering, they're higher still? I don't know how to explain that. Are self-hiring rates higher at particular institutions? We do see slightly higher rates of self-hiring at high prestige institutions. So in other words, at the top of the hierarchy, we see slightly elevated rates of self-hiring. The hypothesis that we have there is that those institutions have in their heads when they're hiring Like we only want to hire the best. We're MIT. We think we're at the top. We're only going to hire from one of our peer institutions, and we believe we have very few peers. So if we can't find a professor to hire from one of these other institutions, we're just going to hire one of our own. We would rather hire from within our own ecosystem than hire from the periphery, from the colonies. And so we think that this is what may explain that. But I'll also point out that these are really complicated by patterns of attrition and by that prestige hierarchy in general. So if you try to decompose higher rates of self-hiring among new faculty versus observing higher rates of self-hiring at elite institutions that may be produced by attrition at other institutions, it gets rather complicated. I think that actually MIT is better able to retain their self-hires and other institutions are less able to retain their self-hires. And I'm picking on MIT, but this is generally true of elite institutions. They're just better able to retain their self-hires and other institutions are not as good at it.